Yeah, secondly, we consider for the antiferromagnetism. Antiferromagnetism is the magnetic ordering like that, the antiparallel spin alignment like this, and down, up, down, up, up, down like this. And here from the in previous J co-positive, Jij positive is the ferromagnet, but in antiferromagnet Jij is negative. Antiferromagnet for the spin Heisenberg spin interaction. From the Heisenberg spin interaction, and this J value is negative in antiferromagnetic interaction, and magnetic moments are nearest neighbor ion lie antiparallel with each other like this. And for simplicity, even though it is not correct in quantum mechanical point of view, and anyway, Weiss model is appropriate for the mathematical formalism, and here Weiss model for an antiferromagnet. The mathematical way is similar from the ferromagnet, but we divide by the spin sublattice, up spin and down spin. Spin up sublattice and spin down sublattice. We divide from the two spin sublattice. And the B spin up is that minus lambda. Here M. That's why is that from the molecular field theory, and the nearest spin affect the magnetic field to the nearest neighbor, and therefore the magnetic here the downspin affected to the spin up case, and therefore here in the down magnetic field on the down direction is coming from the magnetization from the upspin state. Therefore the spin direction is different. You know, and also here this downspin affected to the upspin affected to the downspin, and therefore the downspin affected to the upspin. Therefore the spin direction is different. And here lambda is the molecular field constant. And it is lambda value is negative, and in antiferromagnetic interaction. Therefore, the spin interaction, the magnetization value for the up-down can be write down as ms and bj is a function of the y value is that gj mu b j lambda, but here lambda absolute value, and the magnetization depending on the magnetization over kBt, it is a y value, can be write down like this. And also magnetization value, we define that m up and m down magnetization is the same, the absolute value is same with each other. Then in convenience we can write down m is that ms bj gj mu b j lambda m over kBt. And here the Neal temperature is defined by that gj mu b j plus 1 lambda ms and 3kb. And also it is that n lambda mu effective square and 3kb. The solution is the same from the ferromagnet, and the different thing is that the sign of lambda value. And here, therefore, we know that the solution also can write down here is magnetic susceptibility. The result of the ferromagnetic case, it is a chi value is limiting b is close to b mu 0 over m over b is proportional from the ferromagnet let's write down as a c over t minus tc is a ferromagnet. But in the antiferromagnet, it is the C over T plus Tn. It is antiferromagnet. And because the sign is different. And so Tn means that Néel temperature. Néel temperature is the temperature that the antiferromagnetic order starts. Therefore, from the in general, we write down as C over T plus zeta, capital zeta, and zeta is negative in ferromagnet. And zeta is positive for antiferromagnet. And zeta equal to 0 in the paramagnet. Here, when we measure the magnetic susceptibility, and we draw the picture like 1 of chi versus temperature, then there are three. If we follow the Curie-Weiss law, there is a linear behavior. For example, in the paramagnetic case, and it is zeta equal to 0, it is a paramagnet. And zeta is the intercept along the y-axis, and also here, and the negative zeta value is that this is negative value, and it is zeta is a negative value. It is ferromagnet. And for positives, it is a zeta. It is positive zeta value. It is the temperature. Then for negative zeta, it is antiferromagnet. It is antiferromagnet, and the zeta value is a positive. The positive value is minus zeta. Because here like this. And anyway, from this, it is, we can write down, it is 1 over chi is that T plus zeta over C. And from the plot of the magnetic susceptibility versus temperature, we can think about that magnetic interaction. Yeah, when we apply the strong magnetic field, there is a spin-flip transition. Spin-flip transition means that, in other words, in the metamagnetic transition, and the magnetic spin for antiparallel spin becomes a parallel spin for a high enough magnetic field. Therefore, let's consider for the effect of strong magnetic field. Yeah, strong magnetic field. And also here, the antiferromagnetic interaction case for spin for enough high magnetic field, spin alignments exist. Therefore, in this case, the spin becomes parallel with applying the magnetic field. It is a spin flip, or a spin flip, or a spin flip transition, and we can apply the magnetic field for two directions. And one direction is the B antiparallel direction. It is parallel direction. And let's consider for two cases. When we measure the magnetic susceptibility versus temperature, and there is a antiferromagnetic signal is that Q is low at high temperature, and it falls down at certain temperature. It falls down like this. And also in this case, magnetic field parallel direction, and for the antiparallel direction, and it is constant for antiparallel direction. And also it is a critical temperature for Nil temperature. And here Nil means that the name of physicist who studied for the TN French physicist Nil temperature. And also below Nil temperature, because of the antiparallel spin alignment, magnetic susceptibility decreases like this. For antiparallel magnetic field direction, the antiparallel spin alignment do not affect to the magnetic susceptibility, and that is why the constant magnetic susceptibility. And here, the first one is that the magnetic field direction is antiparallel with magnetization, and for high magnetic field, and the spin rotates. As an angle theta, and in the case magnetic field is parallel to the magnetization. In this case, the antiparallel, and there are spin flip transition. Spin flip transition means that spin configuration abruptly changes. Spin configuration abruptly changes at a critical magnetic field. Here, let's consider for the spin rotated along the field direction, and with an angle spin, it is, for example, it is a spin down magnetization and a spin up magnetization. And by applying magnetic field B, and the angle, it is theta, the angle is phi. Here, spin up, lie at an angle theta to magnetic field, and spin down, lie at angle phi to B. Then, the antiferromagnetic ground state is that theta equal to 0 and phi equal to pi. It is antiferromagnetic ground state. Here is the total energy. Total energy is that we can write down minus mb cosine theta, because energy, magnetic spin energy with applying magnetic field is E dot B, mb cosine theta, and minus mb cosine phi, and plus we should consider for the exchange coupling, and A is the exchange coupling constant, and m square cosine theta plus phi, it is exchange energy between the spin up and spin down. We call it is exchange energy. And also A is exchange constant. A is constant. For the exchange coupling. And also we should consider for the magnetic anisotropic energy. Magnetic anisotropic energy. Magnetic anisotropic energy is that minus 1/2 delta cosine square phi plus cosine square theta. In the antiferromagnetic case, and the theta equal to 0, phi equal to pi. Therefore, energy is that minus mb plus mb minus am square minus delta. Here is that delta is magnetic anisotropic energy, and also therefore is minus am square minus delta. It is natural because in the antiferromagnetic case, spin up and spin down state cancel with each other. We only consider for the exchange energy and anisotropic energy. Then from the spin flip case, is the theta equal to phi. Then the energy is the minus 2mb cosine theta plus am square cosine 2 theta minus delta cosine square theta. Here let's find the angle of minimum energy by derivative with respect to theta is that 2mb sine theta minus 2am square sine 2 theta plus minus plus 2 delta cosine theta sine theta Therefore, when you write down, it is a 2mb sine theta minus 2am square minus delta sine 2 theta. It should be 0. Therefore, sine 2 theta is that 2 sine theta cosine theta. Then here 2mb equal to 2am square minus delta cosine theta, because sine theta cancel with each other. And therefore, the angle of the minimum energy is that arc cosine mb over 2am square minus delta. And this is an spin flap transition. Therefore, when you consider for energy diagram with magnetic field, and this is energy, and actually the energy has this kind of behavior like a spin flap transition. Spin flap phase, the energy diagram can be write down like this. And also from the antiferromagnetic case, there is a antiferromagnetic case, there is an minus am square minus delta square, antiferromagnetic case. Therefore, there is an at low magnetic field. In low magnetic field, antiferromagnetic is more energetically favorable, and high magnetic field and spin flap phase is more energetically favorable. Therefore, here there is the metamagnetic transition for spin flap. We call it is a metamagnetic transition. And if the anisotropic energy is large, for large delta, the spin flap transition is occurred for critical magnetic field. It is a critical spin flap, critical magnetic field, and there is a little bit difference between the spin flap and spin flip. In spin flip, little bit different. Spin flap case, spin configuration suddenly changes, and the spin flip means that spin suddenly reverses a direction, and it is reverses direction, and the spin flap is configuration changes. Yeah, and because we already solved the ferromagnetic problem, then the antiferromagnetic problem can more easily solved in terms of the sign of the interaction. Interaction sign is different.